Welcome to the Explainer. Today, we're going to do something absolutely incredible. We are going to build the entire universe of numbers completely from scratch. Have you ever stopped to wonder what a number actually is? Not just your basic counting blocks, but wild numbers like the square root of 2 or pi. Today, we're stepping in as mathematical mechanics. We're using a brilliant blueprint from a mathematician named Georg Cantor to construct the continuous real number line. And the craziest part? We're going to do it without using any geometry, just simple rules, a sequence of steps, and a little bit of imagination.
Okay, let's dive into this roadmap. We'll start by meeting the number machines. Then we'll be doing math with sequences, comparing our number machines, checking out famous constants, building the real numbers, and finally exploring the foundation for calculus. Let's get to work.
Section 1. Meet the number machines, sequences, regularity, and real numbers. We're going to build numbers using a factory metaphor, starting with incredibly simple parts. Honestly, just like a child's basic Lego set.
So what exactly is a sequence? Well, think of it kind of like a toy Lego machine with a single button. Every single time you press that button, a number pops out. We call the first number A1, the second A2, the third A3, and so on. Imagine you press the button and out comes 1. You press it again, you get 1.4. Press it a third time, 1.41. As you can see, this creates a list. Now, a super common mistake is to look at this and think it's just random noise. But it's really not. It's highly controlled. It's a strict mathematical sequence. So, if our little machine here is building the square root of 2, let me ask you, what do you think the fourth button press makes?
It would be 1.414. And that brilliantly illustrates our next concept, the regular sequence. Imagine two friends walking toward the exact same house. Notice how the physical gap between friend A and friend B shrinks over time? First, they're far apart, then closer still. In math, we say a sequence is regular if it eventually settles down like this. To measure this settling, we use a special symbol called epsilon, which looks like a little curly e. Think of epsilon as a tiny, microscopic doorway they both have to fit through together. It simply represents our tolerance threshold. It answers the question, how close do you want them to be? If we set epsilon to a 0.01 gap, well, the friends eventually get closer than that and they fit right through the door. A huge mistake people make is thinking epsilon is a fixed, permanently set number. It's totally not. It's an arbitrary challenge. If I challenge you to mentally pick an even smaller epsilon doorway, say 0.001, a regular sequence is going to eventually beat that challenge too.
Now imagine our factory machine has been spitting out these increasingly precise numbers. 1.4, then 1.41, then 1.414. The absolute magic in Cantor's idea is that this converging sequence itself represents a solid object. The limit, the ultimate destination of this sequence, is the actual real number. In this specific case, it's the square root of 2. This perfectly fills the mysterious, microscopic gaps in our number line. A common trap is thinking the square root of 2 is just some complicated fraction. It isn't. There's literally no fraction for it. It is the destination of this regular sequence. Now, using that exact logic, what famous number do you think the sequence 3, 3.1, 3.14, 3.141 approaches?
Section 2, Doing Math with Sequences, Wiring the Machines Together. Now, what's really interesting about this next step is that once we have these new sequence machines acting as our numbers, we absolutely have to figure out how to do math with them. If we can't add or multiply them, they aren't very useful to us.
Think of this like wiring two of our toy machines in parallel, right next to each other. Machine A spits out sequence A, and machine B spits out sequence B. To add them, we just add the outputs term by term. It's that simple. In the first column here, the first term is just A1 plus B1. Let's do a quick example. If sequence A is 1.4, then 1.41, and sequence B is 2.2, then 2.21, our addition machine takes the first terms, adds them up, takes the second terms, adds them up, and outputs 3.6, followed by 3.62. Subtraction works the exact same way, strictly term by term. Multiplication, same thing again, we just multiply the terms. Because small changes combined with small changes remain small, these new sequences stay beautifully regular. Division works too, term by term, but with one absolutely critical rule. You must not let sequence B represent 0, because as always in math, dividing by 0 breaks the machine. So if I ask you right now to mentally add a sequence of purely 2s and a sequence of purely 3s, term by term, what sequence do you get?
Section 3. Comparing our number machines, equality and inequality. You'd get a sequence of constant 5s.
Now we have these factory machines producing numbers, but how do we actually compare two sequence outputs to see if they are the exact same number or genuinely different?
Picture two robots walking to a house. They might take slightly different physical steps, but eventually they end up at the exact same front door. In math, we measure the physical space between their metal shoes, written mathematically as the absolute value, an minus bn, and we check to see if it becomes smaller than our tiny challenge gap, epsilon. That is equality. There is literally no gap left. On the flip side, we have inequality. This is when our robots are walking to completely different houses. There is a permanent positive gap between them that never ever shrinks away. These two concepts simply cannot mathematically overlap. Now, a very common mistake is thinking that for two sequences to be equal, they must have identical terms every single step of the way. That's just not true. They just have to arrive at the same destination. So think about it. If there is a permanent 0.1 gap between two sequences' destinations, does that mean they are equal? No way. It means they are unequivocally unequal.
Section 4. Famous constants and examples. Familiar faces. Let's test out our brand new machine rules on some familiar numbers you probably already know and love, just to see how our factory builds them.
What about simple fractions, like 1/3? How does our complex sequence factory handle something so basic? It's simple. We just use a machine that is beautifully stuck on one number. A equals 1/3 is perfectly represented as the sequence 1/3, 1/3, 1/3, repeating forever. If we wanted to represent the number 5, it's just a sequence of 5s. This little trick is necessary to keep our new sequence math perfectly consistent with the old arithmetic rules we all learned in grade school. A lot of people make the mistake of overcomplicating whole numbers in this system. Don't do that. Keep it simple. So, how would you represent the number 3 as a sequence? Yep, just 3, 3, 3. All right, now let's tackle one of the most famously debated topics in all of math. Does 0.999 repeating actually equal 1? Using our factory rules, it is undeniably true. Let's look at step 1. We have a sequence, 0.9, then 0.99, then 0.999. Step 2, notice the difference between this sequence and the number 1. The gap is 0.1, then 0.01, then 0.001. It is shrinking infinitely. Step 3, because this gap drops below any tiny epsilon doorway you could ever possibly name, the sequences are perfectly equal. 0.999 repeating is 1. A super stubborn mistake people make here is thinking there's a tiny microscopic piece missing at infinity. There really isn't. The gap is mathematically 0. Try this out. Can you mentally calculate the shrinking gap between the sequence 0.3, 0.33, 0.333, and the fraction 1/3? It shrinks in the exact same way. Section 5. Building the real numbers. The expanding universe. We are going to zoom out for just a second to see what we've actually accomplished by creating these regular sequences. We've basically built an entire universe. Think of this like upgrading a basic Lego set, because you realized you were missing pieces. First, humans had basic counting numbers. 1, 2, 3. That's set n. But wait, how do you subtract 5 from 2? You can't. So we invented negative numbers, set z. But then, how do you divide 1 by 2? You can't do that either. So we invented fractions, set q. But what about solving a geometric problem like x squared equals 2? There is absolutely no fraction that works for that. So we used Cantor's sequences to invent irrationals, completely filling in the tiny gaps to create the perfectly solid real number line, set r. Cantor's sequences perfectly build this line without needing to draw a single picture. Now, a common mistake is thinking numbers are just physical points on a line drawn with a pencil. Actually, they are precise logical rules. So thinking back to our timeline for a second, what specific math problem were negative numbers originally invented to solve? That's right, subtraction. Section 6, the foundation for calculus. Why this all matters. So the crucial point is, why did mathematicians go through all this trouble to define sequences, epsilons, and absolute values in the first place? It all comes down to calculus. Imagine you are zooming in forever on a curve to find its exact slope. You're taking a tiny step, let's call it h, and you're making it shrink closer and closer to 0. As you zoom in, calculus absolutely requires numbers to get arbitrarily close to one another without falling into mysterious microscopic holes on the number line. If the number line isn't perfectly solid, limits and derivatives completely break down. Our sequence factory is the necessary foundation for all calculus. It provides the continuous road.
A huge historical mistake was assuming that just because a curve is continuous, it must be smooth and differentiable everywhere. It actually took rigorous sequence math to prove that wrong. This abstract math literally powers all of modern physics and engineering. So as we wrap up today, I'll leave you with this provocative thought. If we can build the entire universe of continuous numbers from zero using just basic repeating sequences, what other complex systems in our reality are secretly built from simple, repeating patterns?